Can you see
What
it?
the heck is up there?
Woody, who's up there with you?
Woody, what are you doing under the bed?
Nothing. I'm sure Andy was just a little excited, that's all. Too much cake and ice cream, I suppose. It's just a mistake.
Well, that mistake is sitting in your spot, Woody.
Have you been replaced?
Hey, what did I tell you earlier? No one is getting replaced. Now, let's all be polite and give whatever it is up there a nice, big Andy's room welcome.
What's going on, Drone Dojo here with another exciting project. This is Wally, but you know, as Buster would want you to know, most of the content here to this point has been about drones. We've learned about Pixhawks, we've learned about ArduPilot, computer vision, autonomous missions with Python-dronekit, a ton more. You get the idea. But you might not know this. The exact same hardware, firmware, software stack can be used on different vehicle types. So it's not just drones. So we're talking planes, boats, blimps, yes, blimps, submarines, and rovers. So surprisingly, the learning curve to jump from one vehicle to another is actually super low. Like, it took me 3 years to obtain a lot of this drone knowledge, and it literally took me 3 weeks to port over this knowledge to the Rover. So let me prove that to you. It took me literally 30 minutes to write this precision parking OpenCV script that is running on the Rover that you are about to build. The webcam tracks and automatically drives toward that marker and stops when it's within 1 meter. And, you know, really haven't even scratched the surface of this Rover's capabilities, but that's just giving you a little taste. So learning about ArduPilot rovers unlocks a ton of interesting doors. Here are just a couple examples. This is an autonomous lawnmower running with ArduRover. No, seriously.
Getting very straight lines, and that track there that's unmowed was Skit moving to its initial start point, and
And then here is another example with an actual combine being autonomously controlled from a Pixhawk type flight controller running ArduRover.
Okay, as you can see, I have to navigate around this half ton. Which so far has been possible. Dad's really trusting me here that it's gonna work.
So as you can see, this Rover build might look, ow. So you know, this Rover, Wally, he might look like a basic B RC car, but it's actually an insult towards Wally, you know? It's a bona fide robot. It's not an RC car. Sure, you can control it with an RC controller, but it's a robot. So are you excited yet? Sounded like the SpongeBob opening theme right there. Are you ready, kids?
I can't hear you!
So we're also going to be installing the Jetson Nano to this Rover, making it really the ultimate canvas for any Rover robotics mission. So really, I mean, it sounds corny, but your imagination really is the only limiting factor on this vehicle. So enough talking, let's get into it. In this comprehensive video, I'm going to show you how to go from an absolute beginner to programming your own autonomous Rover missions, which includes a basic overview of ArduRover, how to build the hardware of the Rover, like put all the pieces together into a controllable thing, how to manually drive the Rover, a couple different ways you can do that, how to autonomously control the Rover, both with pure auto mode and with Python scripting, and then how to perform, in the very end, this is our big mission, we're going to perform an autonomous Rover delivery mission. then. And for those of you who want to follow along with the exact same parts that I'm going to be walking through in this video, we actually sell Wally in kit form. We cloned him, and he is available to purchase in kit form. So you'll have everything you need with one purchase. You won't have to find the 50+ parts all on your own. We vetted all these parts, they work, and you get it shipped all together in one box. And you might want to check that out, because after we have a good foundation for ArduRover with this video, in future videos we're going to be doing advanced rover missions on this exact Wally rover. So you can follow along, it'll be very easy, nothing will be different for you. We'll even pre-install all the firmware you need, set up the Jetson Nano operating system that's going to be set up with all the dependencies you need, and even some of the exact same Python-dronekit scripts that we're going to be running in this video and future videos. It's already going to be on your Nano. So all you have to do is build the kit, and then you can drive it and program it. It'll just be plug and play. So easy as it should be, as it should be. Wally, don't you cry. Buster's not gonna fly into you and terrorize. Oh, what's up? Wally's sleeping right now, but like and subscribe this video. I'll wake him up. We'll do some cool stuff outside. All right, now before we jump into the building of our rover, let's just, step back, zoom out, and get a general sense of ArduRover. So what actually is ArduRover? Well, to this point, we've done ArduCopter. Well, we can think of ArduRover as being ArduCopter, but in 2 dimensions instead of 3 dimensions. So you might think this is only land vehicles, but it actually includes boats as well. So boats and Land Rovers. And the conventional term to refer to Land Rovers is UGVs. I'll probably just be referring them as rovers from here on out, but that's something to be aware of, UGVs. And basically, ArduRover is the firmware running on the flight controller, and this is what unlocks the autonomous functionality. This is the separator between an RC guy who just wants to control the car and a robot girl or guy that wants to, program actual autonomous functionality into their vehicle. So now let's get into types of rovers or UGVs. And this might be a little bit overwhelming of a subject when you're first getting into this space. So this is a good framework to view your options through. So you have conventional steering. This is by far the most widely available frame type out on the market. And think of it like a normal car. There is a central engine or motor that's powering the entire drivetrain, right? So these drivetrains are very, very similar. They're basically identical to what's in your vehicle. Like you literally have a drive shaft, a differential, tie rods, all the parts that are actually in a real car on the small scaled down RC car. And then you have skid steering. And this is different because there are multiple engines or motors powering each wheel or track if it's a tank. So you can have one motor per wheel for 4-wheel drive, or only in the back you'll have motors mounted to the wheels if it's 2-wheel drive. These skid steering vehicles are capable of 0 turn, but they are a little bit more difficult to manage and set up. So in our build, we're going to be going with the conventional steering. Like I said, it's the most common type of RC car, easiest to set up, and honestly cheaper. Now zooming in on the conventional steering, we have a couple different frame types. We have conventional RC cars, and that's what is pictured above here. These are designed to maximize speed. Like this one might go 50 miles an hour, which is crazy. And, if you're manually controlling it, that's fun. But for a robot, you don't want a autonomous robot to be flying down 50 miles an hour. So that is a conventional RC car. And you'll notice it's very close to the ground. So it's best for driving on paved and non-bumpy surfaces. Not really that great for off-roading, so they're a little bit limited in where you can drive these vehicles. Then the other type is crawlers. Now in the RC world, they are designed for off-roading and rock climbing. They're not as fast as conventional RC cars, but as I already said, you don't need your robot to be going 50 miles an hour. So it's not as fast as an RC car, but that trade-off there is that the crawlers are very robust. They can drive on basically any type of terrain, everything the conventional RC car can drive on: pavement, smooth surfaces, grass, bumpy surfaces, gravel. Now, in this video, we're going to be going with the crawler frame because, one, we want that wide range of terrain. I want to be able to drive the Rover indoors, outdoors, wherever I need to, and you can do that with the crawlers. And two, like I already said, you don't need these things to drive that fast. The crawlers can get up to 8 to 10 miles an hour, which honestly is plenty for autonomous missions. So we're sacrificing the speed for wider terrain capability. Now we get into conventional steering Rover drivetrain. Now we have like I said, a single, normally it's a brushed motor to provide power, and that brushed motor connects to a brushed ESC to control speed and direction of the brushed motor. And that brushed ESC plugs into the back of the Pixhawk. It'll typically be channel 3. And the steering servo is the other element of the drivetrain. And that is just going to be a servo that's going to rotate the front tires. And that'll plug into channel 1. So it's very simple. You only have 2 signal pins going to the Pixhawk for vehicle control. And most brushed motor ESCs actually have a UBEC on them, so it will automatically power your servo. Now we're getting into the size of different vehicle types. And this size is scaled to the real size vehicle. So a 132 vehicle is very tiny, right? Because it's 1/32 of a normal vehicle. Then you have the 1/8 scale. Really, if you get down to 1/16 scale or 1/14, even 1/12, some of these vehicle types, the vehicle sizes, are just too small to be able to mount everything you need on your UGV. Right, as you see, this is the picture of the Rover we're going to be building. This is a 1/10 scale. And look how, it works, but it's pretty crowded there. You have to be very strategic, even with the 1/10 model, for mounting all the various components, which we will get into in the next section. But it's good to go with the bigger scale in the autonomous UGV space. So our build is going to be the 1/10 scale, conventional steering, single motor, and it's going to be a crawler for all-terrain capabilities. So let's get into it. Let's go build this thing. Okay, it's time to now get into the actual building of the Rover. Now, if you get one of the Drone Dojo Rover kits, you will be getting everything you see here and some more things as well, but all of the same parts I'm going to be walking through in this build you'll be getting in your kit. Now, if you're going to be building your own Rover and trying to find your own parts, basically what I'm showing you here will be extremely helpful for you because you'll gain an understanding of the various components you need to build your Rover, what's required, what's optional. But with that, let's just jump into it. So here is the chassis we're going to be using. This is a 1/10 scale crawler, and this particular one has the motor already built into the chassis. We have a waterproof component to place the RC receiver in. And then you'll need 4 tires, and then a brushed ESC if you're using a brushed motor. And this can plug into our flight controller and it will drive our motor. This is our steering servo. This is going to literally steer the vehicle for us based off of our commands. Then we'll need a GPS mount, a lot of zip ties, and various strengths of sticky tape. Then you'll need a PPM encoder, and that is to take the output of the RC receiver, feed it into the PPM encoder, then that will be able to communicate all those channels with this one line into your Pixhawk. We're using a Pixhawk in our build, and you'll need a 4 gigabyte SD card. That's required to do the ArduRover stuff. Here, you have a choice. You can use you don't even need a companion computer, but if you do want one, you could use a Raspberry Pi or a Jetson Nano or anything else. We're going to be walking through the Jetson Nano because I just think that's a good choice for the Rover vehicles. And with that, you'll need a 64 gigabyte SD card. But this is optional, the companion computer, but it does unlock some very advanced features of your Rover that you can't do on just a basic Pixhawk. Then you'll need a way to mount your companion computer to the frame. Here is a custom designed and 3D printed mount that works specifically with the Jetson Nano. Moving on, here we have the Wi-Fi telemetry module, and this will plug straight into the Pixhawk. And this is our companion computer to Pixhawk connector. Moving on, this is our power module. It's a lot of stuff going on here. This is a basic power module. This is what it looks like. You'll notice this is the XT60 connectors on either side. For the Rover world, you're going to want a Dean's connector power module on either side. So that's the red one. And then how are we going to power our companion computer? Well, we're doing that with a UBEC. The Jetson Nano requires a 5 volt, 3 amp power supply. So this is just soldered onto the power module. And at the other end of this UBEC is a USB-C connector, which is what powers the Jetson Nano. I'm not going to show you how to do that. There's plenty of soldering tutorials, but I will show you some more details of that when we get to that point. Next, we have the battery charger, LiPo battery charger, the LiPo battery. Then we have the RC controller. I recommend you get something like this. There's the wheel model of RC controller too that looks like this. I don't recommend using one of those units. I do recommend using something like this. This is the FlySky i6 that comes with the kit. You can actually modify it to become, I believe, an 8-channel transmitter. Then moving on, this is the webcam we are using in this build. It has pretty good resolution and a built-in mic, which might be cool for some voice control in the future. And then we have optional a mini servo that you can wire into the Pixhawk to hold on and let go to things, kind of like what we did with the Taco Copter. Okay, this build section is actually going to be split into 2 different sections. In this first section that we're starting on, what we're looking here is the bare essentials to get this crawler chassis driving. This is very surprising. All we need is a RC receiver, steering servo, motor ESC, motor, and tires and the chassis. And we're going to get the vehicle drivable with all of these components first. And that's because we're going to be doing some tuning on the chassis. We need to make sure the vehicle drives straight, make sure the wheels look good. And then after that, we'll go into section 2 of this build section, which will be putting all of the advanced parts onto the chassis to make it an autonomous vehicle. Now, the very first thing we should do before anything else is make sure that these wheel bearings are installed. Now, in most of your kits, they should already be in the little hub, but sometimes these wheel bearings can fall out. So just on each one, just kind of press it in there. Make sure it's flush with the outside surface, and only after that wheel bearing has been pushed in should you install the hex nut and that little pin. On the tire side, there's one side that has a little hex slot, the other side doesn't. The hex slot is going to be towards the wheel mount. Okay, and then on the wheel mount side, you see there's a little hole there. We're going to slot in a pin. So this is our setup here. We're going to slot in the pin to that hole. On the other side, we're going to place this hex nut, and you see the perforations there to fit that pin, and that's just a press fit. And then the wheel snugs onto this hex nut. Then on the other side of the wheel, we tighten down with this M7 nut. And we're going to do that for all four of the wheels on this guy. So let's get to it. And with that hex nut, you want to rotate it around and press down. It's just a press fit, like I said, but press down so there's no space between it and where it's mounting to. Then once we have that, we just place the wheel on there. And on this side, we just thread in that M7 nut. And I would just start out getting it hand tight. And then once it's in there a little bit, we can get our M7 socket set and tighten that down. Now you do not want to over tighten and you do not want to under tighten. I would just, with a small size socket wrench like this, tighten it down so where you're getting some pretty good resistance, and then go to the very end of that small socket wrench and then do maybe 1/8 of a turn. And there we go. And you shouldn't see any wobbling in the wheel hub now. It should be pretty solid there. You will have movement in other places of the drivetrain, but as far as the wheel in the hub, it should be pretty good. Okay, then after we have all four of those wheels installed, the next thing we're going to do is install the steering servo. Now the steering servo is obviously going to be on the side where the wheels can turn. So the Drone Dojo kit comes with this servo mount. Now there's a smooth side to this mount and a non-smooth side. The non-smooth side is counterintuitively facing up, and it just slides in here on this frame, and then you can bolt it in later. Before we do that, what we're going to do is install the servo. So that you see there's 4 mount points here on the mount, and then there's 4 mount points on the servo. Okay, now imagine the driver is facing us. So we need the servo line to be pointing that way. So we're going to mount the servo like this. All right, because this is going to slide in like this into the vehicle. And first thing, it can be a little hard to start the thread, but I'm just going to get these started. I'm not going to secure them down all the way. I'm going to get all 4 started, and then I'll start securing that down. So that started pretty good. I'm going to get the other 3 in now. Okay, then when you're finished, it should look something like this. It's down secured with all 4 screws in. And then this little servo mount, very simply, just slides in. There we go. It just slides in there. And then once that is slid into the chassis, we can secure that down with 4 of these screws. There's little mount points on either side of this frame, 2 on this side, 2 on that side. So let's secure these down now. I'm going to do the same thing, just get all 4 of them in just enough. And then after I have all 4, the thread of the 4 started, I'll start tightening them down. You might have to do some finagling to get the screws to slot into the mount points on the servo mount. Like for example, this last screw I had to pull up on this servo mount to get the hole to align. So, all right, now there we go. That servo is installed to the servo mount, and that servo mount is installed to the chassis. Okay, next we're going to mount the brushed motor ESC to the frame. First, we're going to though look at this switch here. It's an on and off switch, and it actually slides into this little slot right here. So you just go up, press down, and there you go. So now your on-off switch is mounted. Now we're going to mount the actual brush motor ESC to the frame. Now on the left side you have the receiver box. On the right side, that's where we're going to put the brushed motor ESC. Then we'll just have it like this, so the signal side comes out towards the front of the vehicle. And for this, you need some heavy-duty Scotch mounting tape. So I'm going to remove that. Get off of me! And then remember, we want the signal line to be pointing this way, so we're going to mount it just in the middle. There's a little drop down here. We're going to mount it in the middle of that. Just press down, and now that thing is locked. Now we need to combine the motor that is already on this chassis with the motor driver, our brushed motor ESC. So we have 4 different lines coming out. 2 of those are going to connect to the battery to supply power to the vehicle. The other 2 are going to connect to the motor. And these are very simple connections. They just plug right into one another. You're going to attach red to red and black to black, and just press that in. And there we go. You want to push that in so that the motor bullet connector is all the way inside of the connector on the motor ESC. Now we'll do that with the black one too. And there we go. We have our motor now connected to the motor ESC. And this is going to plug into the Pixhawk. So the Pixhawk is going to send a signal here, which is going to translate to a signal on the ESC, which is then going to drive the motor. Now remember, this is just the first part of the build, so we're not really worried about securing everything down exactly how it's going to be. We're just trying to get the vehicle into its minimum viable driving state so that we can test the straightness and tweak the tie rod length to get it to drive really straight. So with that in mind, we're not going to mount the RC receiver yet. We're just going to take the servo wire and plug that into channel 1. Channel 1 is going to be on the very bottom. And the signal pin on the servo is the yellow and ground is brown. So signal is closer to the middle of this receiver. And then let's go ahead and connect the brushed motor ESC to the receiver. And white is signal on the brushed motor ESC. And let's connect that actually to channel 2. And I'll show you why in a minute. Normally throttle is channel 3, but just for this initial drive, it's going to be connected to channel 2. We're going to want to change this later. Underline what I just said. We're going to change this later. Okay, now with everything wired up to the receiver, let's go ahead and plug in our battery. And you won't hear any noise at first, and that's because our switch for the motor ESC is in the off position, so put that on. And you hear the beeping, which means we're now live. So, turn on the RC controller, and you hear another beep. So, currently, I should be able to control the throttle of the vehicle. Now, channel 2 we set up to be the throttle, and channel 2 on this setup happens to be this switch right here. And as you can see, I'm actually able to move the vehicle with this switch. So that's good. We now have very basic control. Oh God. Basic control of the vehicle. But one problem, right? We have not configured the steering servo yet. And why is that? It's because we didn't know how to mount the horn of the servo until we knew what the center position is. So once we turn on our RC receiver, channel 1 is horizontal on the right stick. So that right now it's in exactly the middle position. So that middle PWM signal is being sent to the servo. So right now we know that the current position of the servo is neutral. It's right in the middle. Okay, now that we know the center position of the servo, it's currently in the center position, we can actually mount our servo horn. Now there's 2 sides to this. We have this side and then we have this tooth side. This is going to be the side that is facing the servo. And then there's two ways to secure this down to the servo. You have these two little tighteners on the side here. And then we also have a set screw that we'll place directly down the center here. So, but first, let's just place this so it's almost as perfectly center as we can get it. This is about center here. And this servo comes with a little set screw. So we're just gonna thread that in here. There we go, that's pretty secure. And then to get those little screws on the side, we need a little M1.5 hex key. And this doesn't have to be insanely tight, just, you know, just tight enough to where we have a good secure servo horn. Now we need to actually connect this tie rod to the servo, the steering servo, because that's what it's doing, right? It's steering. So what's going to happen is the servo will turn this way and it'll turn the vehicle. And then we can also turn this way. So let's go ahead and secure the tie rod down to the steering servo. And we can do that with an M2.5 hex key screw. And this is about 1 centimeter long. So this is going to just press fit through the first part of the tie rod. And then the rest of these threads are going to thread into the horn of the servo. We can tighten that down a little bit. I'm going to press left on my RC controller and it turns it left. Now, if you look at our back two wheels, they look pretty straight, right? They're pretty parallel. But our front wheels, they're a little off balance. It's kind of like they're kind of bowed in a little bit instead of straight like this. So we can actually fix that by extending this rod right here. Right? They're kind of bowed in right now, and if we extend that rod, they'll slowly go straight. And to extend this rod, we actually have to unscrew it right here. So there we go. This is removed now, and if we turn it counterclockwise, we can actually lengthen this rod. Now let me just go too far so you see what will happen if we go out too far. So they were a little bowed in before, now they're going to be really bowed out. See, if I try to place this back here, you can see now the wheels are bowing out. So that's too much. So before it was too little, you don't want to go too crazy in either direction. It's really a process you want to take your time with. So I am going to leave mine about like that, because the wheels weren't too badly bowed in. So I'm going to secure that down. Now I'd say that looks a lot better. It wasn't too bad before, but that looks almost perfect. Okay, the next part we're going to be focusing on in this build is making sure our Rover drives relatively straight. We can do this by adjusting the length of the tie rod on our Rover that connects the servo to the two front wheels. So we're going to start out with the tie rod tightened down all the way, but we want to get our Rover aligned so that it drives relatively straight. It doesn't have to be perfect, but you want it to be pretty straight. Okay, this is test one. I'm going to drive without steering and see how straight this thing is. So as you can see, that pulls to the right pretty hard. So I'm going to adjust that tie rod and make it a little bit longer. And I'm just going to lengthen it by a few turns and then see if it starts to drive a little more straight. So there's 1, 2, 3. I'm going to try that out. All right, test 2. We lengthen the tie rod a little bit. Let's drive forward and see how straight this is. So it's definitely better. So we're gonna lengthen that tie rod just a little bit more, not as aggressively as the first time, but maybe just a couple turns, and we'll try it out again. All right, this is test 3, just lengthening the tie rod a little bit more. Hopefully it goes straight and it's not veering to the left this time. Let's try it out. So we're still a little off. We could probably go another turn or two. All right, here we go. Here's another test. And as you can see, that was pretty good. It might have started out aiming to the right a little bit and then drifting to the left. Now, how many of you have gone on the highway, you know, you take your hands off the wheel and you see how long the car can go straight for before you start to panic because the car starts drifting? I might be the only one, but you will notice that if you let go of the wheel on the road, your car starts drifting. And that's because, just like we were dealing with our little Rover, the tie rod lengths aren't exactly perfect. But they don't have to be perfect because they have a human pilot accounting for the errors, right? Starts to drift a little to the right. Your brain's like, oh, let me pull to the left. Well, similarly with our build, we don't need to get it perfect. We want to get it as close as we can to perfect, but it doesn't have to be perfect because we're going to be running the control through the Pixhawk, or the flight controller. And this is going to be like analogous to the human in the real car example. If the Rover starts to drift a little bit to the left, the Pixhawk, the flight controller, will pick that up and be like, oh, what are you doing, Rover? Let's shift you back in this direction. And that'll happen automatically in the autonomous mode. So we don't have to worry about getting this perfect. Just get it as close as you can, but don't obsess over it. Have I made it clear yet that we offer complete Rover kits for you to build yet? I don't know, but here's Wally. So funny thing about YouTube is that after you publish a video, you can actually slice out parts of it. So this part is going to get sliced out at some point. If you're watching it, obviously it hasn't been sliced out yet. But if you are one of the early Rover purchasers, you're also going to get, in addition to everything else that comes with it, a free video consultation with me. So if you have any questions about the Rover, any missions you have in mind, and you want to kind of brainstorm about the technical aspects of it, a free video Zoom call with me is going to come with your personal Wally as well. So if you're watching this, the offer still stands. If not, then you had no idea about this anyway, so... Okay, so after that alignment is done, we have completed the part 1 of our build series. Now that we have the alignment pretty much straight, we're going to start actually fixing the various pieces to our frame. You notice here there's a little box that has 4 little screws. That is where we're going to put the receiver and PPM encoder inside of. It makes it semi-waterproof. So let's go ahead and take that off with the M2.5 hex key. That's where our receiver wires are going to be hanging out. Now let's unplug what we had plugged into the receiver. We're not going to need that anymore. So the RC receiver has 6 channels. And what this PPM encoder does is it takes the 6 channels, and you see all these wires. It takes that and puts it into just 3 wires. So it makes cable management much easier. So the channels on the PPM encoder start with the white being channel 1, orange being channel 2, and so on. So we're just going to plug that into the RC receiver with the color code, just like that. So then we go to orange and so on. There we go. That's what that will look like when it's done. Now I'm just going to wrap this around once, and I'm going to put 1 piece of normal sticky tape on the back of the PPM encoder. All right, there's our finished product, and that is ready to place inside of that little hub that we opened up right in here. There we go. Our receiver is protected in this little box, but we have access to everything we need on the outside. All right, next up, we're going to assemble the GPS mount. Now it's pretty straightforward. Here's the base of the mount. We'll start out installing this piece here. And you'll see one side has a side for the head of a screw to go into. The other side doesn't, so just make note of that. And we're going to screw in this piece right here. There we go. And you'll see there's a little hole in there. That's going to be the set screw. So now we're going to take our pole here, and you see there's a shaved edge right there. That's going to be facing the side that the set screw is going to be screwed into. So there we go. That should lock that pole into place. Now we're going to take this piece and slide it on down. We can go ahead and tighten that down. There we go. Now this isn't so wobbly. Now we're going to take this piece, and there's another little shaved edge on the other side of this pole, and another set screw on this piece. Hard to see there. But make sure those are facing each other, and then we'll screw in the set screw again. There we go. So this is the mount side that'll go onto the frame, and then here we're going to put a piece of sticky tape. There we go. And we will keep this side on until we have installed this GPS mount to the chassis. Now you can get creative with where you want to mount the GPS on your chassis. Maybe you don't even use one of these conventional GPS mounts. That's what I'm going to be doing for this build, however. So what we're going to do is secure it with a simple little screw. I think this is an M3. So there's a little hole here. So I'm going to screw this in through the hole, and then this will actually thread into the bottom of the GPS stand. There we go. We have broken through to the other side, so now you should just be able to take this mount and just thread it in. Then we can mount our GPS module to that GPS mount. Now this is going to be the front direction of the vehicle. You see there's a little arrow on the GPS. So once we take this off, make sure to align the front of the vehicle with the front of the GPS. And there we go. Our vehicle has GPS now. All right, so next we're going to install our Wi-Fi telemetry module. And I'm going to place mine right here. Before you mount it though, you should make note of what's on the back, because there's going to be some crucial information on the back. So SSID, that's going to be the name of the Wi-Fi network we connect to, then the password, Alpha UAV link, then the port we connect to will be 14550. This might be different depending on what your Wi-Fi module is, but definitely make note of what's on the back before we mount it so you don't have to unmount it to see what the heck your password is. And then we want this connector to be facing the inside of the vehicle because that's where the Pixhawk's going to be. Maybe even take the antenna here of the Wi-Fi module and just place it in one of those holes of the GPS mount. All right, next up we're going to mount the Pixhawk to the chassis of the vehicle. We're going to do that with this super duper mounting tape. I'm going to use two pieces here. Let's stage out where we're going to put it first. This is pointing towards the front of the vehicle. So steering is up here, so we want the arrow of the Pixhawk to be pointing this way. And let's make sure the Pixhawk is in about that area. We want enough space back here so that we can actually plug in our servo pins to the rails on the Pixhawk. And if we're too close here, we won't have access to that. So make sure there's a little bit of space there for the Pixhawk. Let's stage that out. Okay, we'll place it around there. I'm just gonna fix this tape to the Pixhawk now. There we go. Let's go ahead and place that on the frame now. All right, then when we're happy with how that looks, we'll just go ahead and press down on that. Lock that in place. All right, next thing we're going to talk about and install is the power module. What is the power module? Well, we know we're powering our vehicle with a LiPo battery. And this is what a normal power module looks like. It has XT60 connectors. One side connects to the battery. We'll have a wire that will be coming off of the power module, and this will power your Pixhawk. And then the other end will power the vehicle. In our case, it'll power the motor ESC. Now you notice right away that the battery and the power module don't have the same connector, so you can bridge that with a Dean's to XT60 adapter. But what would be better is if we just got rid of this and got a power module that had a Dean's connector on each side. That's the red connector, also called a T-plug at times. But we're also going to be needing to make some more modifications to this power module outside of just the connectors. And that is because we need to power the Jetson Nano. Now the Jetson Nano takes the power input here at the USB-C adapter, and it needs a 5 volt and a 3 amp power supply. So how are we going to power this thing? Well, it's going to be a little bit tricky of a process. We're going to make some mods to the power module. So here is what we call a UBEC. It inputs a voltage from 5 volts to 23 volts and outputs a 5 volt 3 amp power supply. So that's what this is, right? So this is the battery side, goes into the power module. Then on the outlet, we soldered on this UBEC. But the problem is we still don't have that USB-C connection, so we also have to solder this end to a USB-C power cable. Can be a little bit of a tedious process, but at least you know what you need to do. Kit purchasers actually have this pre-soldered and pre-put together, so you guys don't have to worry about this. Okay, so that about wraps up the installation of the various parts. Now let's start wiring everything into the Pixhawk, the central control unit. So first, let's start out with the servo. So we have this big long servo wire. So we have aux out and then we have main out. We want to plug in this pin to main out the first slot. Here we go. So the Pixhawk will be controlling that servo, the steering servo, through aux out, or main out 1. And then next up, we have the brushed ESC. Here signal is white, and this is going to plug into main out 3. Now remember that PPM encoder, well, that is going to plug into this RC column right there. There we go, that's what the back of the Pixhawk will look like. Now let's start wiring in everything to the connections on the top of the Pixhawk. So let's wire in the GPS. There's actually a slot called GPS on the Pixhawk. Plug that in there. And then plug in the other cable to the I2C port on the Pixhawk. This is actually the external compass. Next we have the Wi-Fi telemetry module. We'll place that in Telem 1. Here we go, we have GPS, I2C, Telem 1 for the Wi-Fi telemetry. Next up, let's install the power module. Now, the end that has the Pixhawk connector on it, that's the side that the battery plugs into. And the battery is going to be coming from the back end of the vehicle. I'm just going to slide this up here. Then the battery will plug into this. Now we need to connect the motor ESC to the other end of the power module. And this will be a static connection. We'll never change that. And then the cable coming off the power module needs to plug into the power port of the Pixhawk. It'll plug into this port, and now our Pixhawk is getting power from the battery from the power module. And now we're going to install the buzzer that will provide some helpful audio feedback to us. It'll go off whenever we arm the vehicle, for example. To do that, we're just going to take a piece of this double-sided tape, and then, you know, you can choose where you want to put this. I'm going to put this at the very front of the Pixhawk, and don't cover up this buzzer port, because we need to plug that in. There we go. Next, we are going to install this little connector. It connects the Pixhawk on this side to the Jetson Nano on this side. And this will just plug into Telem 1 or Telem 2. Right now we have the other Telem port plugged into the Wi-Fi telemetry. There we go, and we'll plug this in after we install the Nano. All right, now Wally needs some eyes, of course, so we're going to install this webcam that also has a mic in it, which will make it handy for future projects. Where are we going to mount this? Well, we want it to be the front of the vehicle so we know where we're driving. So on our Wally kit, I recommend mounting it right here on the back of this servo. So it'll sit something like that. And I'm going to do that with the mounting tape, the red mounting tape. Put it on this side of the webcam. There we go. Now I'm just going to try and mount that as center as I can on that servo. It's actually a really nice fit there. Make sure it's flush and then just kind of press it down. Now Wally has eyesight. And, you know, if you're driving in some bumpy terrain, you can always fix this camera down so it doesn't jump on you. If you're driving on smooth terrain, you don't have to worry about that. And this extra cable length, you know, you can choose to trim it if you want, but it actually stays pretty nicely right there. You could also choose to zip tie it down if you want. But then the USB cord will plug into the Jetson Nano whenever we install that. Okay, now we're going to mount the Jetson Nano to the chassis, but it's kind of an awkward piece. It's difficult to mount. There's not a lot of good mount places on the chassis, so that's why the drone Dojo kits are going to come with this custom mount. This is a really cool mount, kind of looks like an elephant. A good friend Hutton designed this. Here's how the Jetson Nano will fit on there. It aligns with the mount points on the Jetson Nano. And then it will mount onto the vehicle by slotting into these two holes here on the frame. And it'll just press in like that. And that elephant trunk part is actually designed to rest on top of the Pixhawk to provide some extra support. And it should be covering up the switch pin, which we don't need for the Rover builds. The mounts that will be in your kit will have holes on the back, on the bottom here of this mount that you'll take a hex key and just sort of torque that down on either side. You'll notice we still have access to all of the pins of the Pixhawk after the Jetson Nano is installed. And that was because Hutton's design raised the Jetson Nano up a little bit so that everything is still accessible. So how will that look with the Jetson Nano? It'll look just like that. We're going to have our peripherals, our input to the Jetson Nano facing the middle of the vehicle. So that's how it'll look. Let's secure the Jetson Nano to that mount. Now you'll want the elephant trunk side to be towards the USB ports. And it secures down with M2 screws, and they should be 6 millimeters long. So let's go ahead and secure that down. There we go. That's what this will look like after the mount is installed. So let's now attach that to the chassis. And now on your mount, be sure to take an M3 screw, put it into the bottom of this peg hole and screw that in to the mount so that it is now secure to the frame. Just thread that in with a hex key. And then that camera USB, all you have to do is plug it into one of the ports. Now you got a camera feed. All right, then we will take that USB-C that is coming off of the UBEC on the power module, and we'll just plug that into the USB-C port of the Jetson Nano, and then our Jetson Nano will be getting power. All right, so before we move on to the Jetson Nano, you might notice we have a wiry mess. And that is why we supplied you with a plethora of these zip ties. Zip ties are your friend on this build. So we're gonna just spend a little bit of time securing everything. And I mean, there's no right way to do this. This is just gonna be whatever your preference is. There we go. Now the build looks a lot nicer. You can be creative with how you want to use your zip ties. This is the battery connector. So it needs to be close to here, which is where the battery is going to sit. All right, it's going to sit something like this. So however you mount the power module, it needs to have enough slack to get to the battery. And then one note about how to secure the battery. I mean, this works pretty good just with one simple strap of Velcro. All right, now we're going to flash the Pixhawk with the firmware, in our case, ArduRover. Go ahead and open up Mission Planner, and if you don't have Mission Planner, literally just Google Mission Planner, and you'll find a download screen. We're going to go to Setup, Install Firmware, and here is where all the magic happens. So we're going to select the COM port associated with our Pixhawk. If you haven't already, plug in a micro USB cable to the Pixhawk and plug that into the computer. And don't hit connect. We're going to leave this disconnected, but find that COM port for that USB that you plug in. Now we're going to select the vehicle type we want to use. And everything displayed here is the latest. If you wanted to find an older version, you could go to all options and then find whatever version you wanted to use here. Of note, I already do have the micro SD card slotted into the Pixhawk, and this will not work if you don't already have that in there, so go ahead and do that if you haven't. I am going to just go with Rover 4.1.0, and it'll prompt you, are you sure? Yes, yes. Platform, aka the flight controller. Ours is Pixhawk 1, and then just hit upload firmware. And it's going to download this from the internet first. Then it's going to erase the old firmware and try to load up some new firmware. Now it should try to automatically disconnect the USB cord and reconnect. If that doesn't happen, it might get stuck here for scanning COM ports. So if you're stuck at that point, just manually unplug the USB cable and plug it back in. There we go. About 30 seconds later, the upload is done, and you should see a flashing light on the Pixhawk. At this point, you could connect to Mission Planner, do that, and then we can confirm that version under the Messages tab in Mission Planner. So go to Data, Messages, and here we go. We have ArduRover 4.1.0. So I'm not going to cover this here because there's a ton of resources online to do this, and it'd be kind of redundant, but once you first set up your Pixhawk with firmware, you need to do a couple calibration steps for various sensors. So go to Mandatory Hardware, and you need to do Excel calibration, compass calibration, radio calibration, and that's about it for the mandatory stuff. You could do battery monitor, but definitely these three you'll need to do, and I'll link in the description for the documentation on how to do that. All right, now we are going to connect to the Wi-Fi telemetry module, and it's very, very easy actually. So I'm going to pull up my current networks. You'll see Alpha UAV link is currently not online, but for my module, this is the name of the module. So I'm going to plug that in, and a couple seconds after that, that should be a very strong signal, and I'm plugging into Telem 1. And again, the network that you need to connect to will be on the back of your Wi-Fi telemetry module. So I am going to click on that and connect. And while that's connecting, I'm going to open up Mission Planner. And here we go. Mission Planner is automatically connecting to my Pixhawk through the Wi-Fi connection. So how would you do this if it didn't automatically boot up? You would click UDP and then select your baud rate. You can actually select that if you try to connect once and X out. Select your baud rate. Mine is 921600, and then hit connect, and then enter the local port that your telemetry module is broadcasting on. For me, it is 14550. This will also be on the back of the telemetry module. Then hit enter there, and then the connection should start. And now it's very simple. You're just connected to the Pixhawk with Wi-Fi instead of the conventional 915 megahertz radio signal. So there we go. That's pretty much it. If you're having any trouble connecting, you might need to change a couple parameters. First is go to BRD, BRD SER1, and make this 0. It'll be default 2. And then go on to serial 1, and then change the serial baud to 921, or whatever your Wi-Fi telemetry module says. All right, so at this point, we should have a Rover built, not yet ready to drive. There are some things we have to set up on the Rover before we can start driving it. Trust me, you don't want to just jump into driving the Rover. The first things we have to set up is related to the remote control. So I am demoing on a FlySky i6 RC controller. So on a drone, you have 4 channels you have to worry about, right? Roll, pitch, yaw, throttle. On a Rover, really you only need 2 channels for controlling the vehicle, and that is going to be roll for steering and throttle for going forwards and backwards. Conventionally, on a RC controller, you have one stick that automatically centers to the middle, and you have the stick that stops wherever you let go. This one is typically the throttle stick. The problem with that on a Rover is we need the throttle to be able to go forward and backwards, but with this throttle stick, we can only go forward. So we need to map the throttle control to this stick, the one that centers automatically to the middle. So I'll show you how to do that. First, we need to find out which channel this vertical axis on the centering stick is. So it'll be different for you depending on which controller you have, but I'll show you that on the FlySky FSI6. Hopefully you can see that. You're going to go to System, kind of hard to see upside down. Scroll down to Sticks Mode, and we'll see which channels are mapped to the individual axes. So we see our centering stick is channel 2, so we need to make channel 2 the throttle on our Rover, and the steering, oops, let's change that. The steering is channel 1, the horizontal axis on our stick over here. So let's go ahead and set that up. All right, now we have the Rover connected to Mission Planner, and let's go ahead and make those RC adjustments we were just talking about. So very simple to do. All you do is go to Config and then Full Parameter Tree, and look for a parameter called, hey, okay, stop it. Look for a parameter called RC Map. There it is. And remember, we want the throttle control to be on channel 2, or at least for my controller, for the throttle to be on that automatic centering stick. It's channel 2. So all we have to do is hit RC Map throttle and enter in a 2 here. And then so we don't overload channel 2, let's go ahead and change RC Map pitch to channel 3. And remember, we also wanted roll to be on channel 1, because roll is the steering control on a Rover. Well, that's already set up as channel 1 for us, or for me. It might be different for you. So get the RC map the way you want it, and then all you have to do is hit write params. And it's really as simple as that. Now we can control the throttle on our Rover with channel 2, which is awesome because we can go up and we can go down to go backwards on the Rover. Okay, now that we have our RC stuff set up, it's time to set up something that is very, very important, which is the motor spin direction. So how do we test that? Go to Setup, Optional Hardware, and go down to Motor Test. Now kind of hold the Rover up in the air a little bit, put the throttle to 15%, and the motors, whenever you hit Test All Motors, the wheels should start spinning forward, right? So we're going to click that. And as you can see on my Rover, the motors are actually spinning backwards. So the firmware is trying to move the motors forward, but the motors are spinning backwards. So we fix that by going to mandatory hardware, servo output, and then look for, here we go, throttle, and just click that checkbox, reverse. Yours will be like this. It won't be checked. Check that checkbox, and then head back to motor test. And one thing before we go back there, it's a little confusing, right? Because we set throttle to be channel 2, but this is under number whatever that means, 3. Ignore that. Just reverse here, and then go back to motor test. And now that we've reversed the throttle, whenever we hit test all motors, the wheels should now start spinning forward. And as you can see on my build, that is now the case. This is something that is extremely important to get right, because some of the drive modes are dependent upon knowing which way is forward, right? So in auto mode, if you try to tell the rover to drive from one waypoint to another, and it tries to drive forward, well, if you have the motor spin direction wrong, it'll actually rocket the rover in the wrong direction. And it can be kind of tempting to fix the motor spin direction in other ways, like I tried to do, maybe, or maybe not. Like, you might be tempted to go to the RC parameter, RC2, and be like, well, what if I just do RC2 reversed and put a 1 here to reverse that RC channel? Yeah, that doesn't work. You might be tempted to just change reverse the signal on your RC controller itself. That doesn't work either. You absolutely have to change the motor spin direction under servo output and checking the reversed checkbox. All right, now after we get the motor direction situation figured out, there's another thing regarding the motors we have to test, and that is the dead zone. So you might have noticed whenever you input a percentage of throttle and tested all motors that the motors didn't spin at all. Or in my case, the motor. There's only one motor. So maybe then you went up to 10 and you hit test all motors again and it didn't go. And then finally you got to, let's say, 15% throttle. You hit test all motors and the motors were barely spinning, but you found that anything past 15, the motors will spin. So that will be different on every single build. And you need to identify this dead zone, because if the motors don't start spinning till the throttle is 15%, that means you move the throttle 15% and the motors won't react at all. The lowest throttle percentage required to get the motor to spin the wheels at all, you need to find that. In my case, mine was 15. Go back to config and then find MOT for motor, and then MOT underscore throttle underscore min, and then write in that percentage here. So mine was 15, so I'd write 15 and then hit write params. And then after that, you should be able to go back to motor test. Now put a 1% throttle, test all motors, and all the wheels will start spinning at that 1% throttle now. Okay, so now the rover is basically ready to drive in manual modes. That is, modes where you are controlling the drone with the RC controller and you're in manual mode. There is one thing you do not want to skip if you plan on doing autonomous missions with your rover. So go over to config and basic tuning. Now, if you come from the world of ArduCopter and you have a drone, you might have been familiar with the auto tune mode, which is a mode that finds the optimum PID gains for the drone. Unfortunately, with Rover, there isn't a mode or a way to automatically find these optimum PID gains. You actually have to do this on your own. There is some pretty good, got to give some respect to Yay, Jail Part 2, Donda, good album, check it out. There is some pretty good documentation on this subject on ArduPilot's website. So we have the tuning turn rate, a lot of good stuff here. And then we have the tuning speed and throttle page. So you'll definitely want to follow these two guides, and those help you find these PID gains that you enter in here. and gets some really nice control on your rover, and you really want that before you're doing autonomous missions. It can be a little bit painful because, I mean, the documentation is a great place to start out, but it's a little bit old and there are some holes that you need to figure out on your own. It actually took me, gosh, about an entire day to figure out how to tune my rover, but yeah, just be prepared for a little bit of pain there. For kit purchasers from the Drone Dojo, your rover is going to come pre-flashed with the optimum PIDs for steering and throttle. So you actually don't have to worry about this tuning if you're good with the gains that I am using, which is pretty decent out of the box. All right, now let's just set up a couple miscellaneous parameters. One thing that is nice to do on rovers is disable the safety switch requirement. So go to BRD, where are we at? BRD safety enable. Yours will likely be 1. Go ahead and change that to a 0. Now let's set the speed of the RTL mode. We'll learn a little bit about that later. Right now, just change RTL speed to 1 meter per second. That's roughly, 2.5 miles an hour. Now go to WP and change WP speed to 1 meter per second. I think 1 meter per second is a good starting point just because it'll work for a wide variety of rover types, and you can always raise that later if you need to. So set all those and then hit write params. And again, kit purchasers will have all of these and more parameters preset, so you don't have to worry about a lot of these. You only need to change the things that you want to change. Okay, this is the last thing we're going to talk about before we actually start to drive the rover, and this is rover control modes. So there are different modes that you can control the rover from, like acro mode, guided mode, hold mode. All these provide different functionality, and we can actually switch to different modes from our RC controller or other sources. So we're going to set up the mode changing system on our rover. So with the rover still connected to Mission Planner, go to, actually let's start out in setup, mandatory hardware, radio calibration. Turn your RC controller on and turn one of your knobs. Look for channel 5. You want one of your knobs to be on channel 5 because that is what we're going to configure our control modes on. So once you identify which knob is channel 5, we can move on to the next section. If channel 5 is not currently a knob, maybe it's a switch, you can change that on your FlySky or whatever RC controller you're using. Okay, so then after we have identified a knob using channel 5, we need to configure that again with parameters. We're going to go to mode channel. So I think yours will be set to channel 8 by default. Let's change that to channel 5 and then hit write params. Okay, so the way this works, the range of a pulse width modulation signal is from 1,000 to 2,000. So different chunks are going to change the rover into different drive modes. So which drive modes? Well, now we go to setup and flight modes. And you see here so flight mode 2, manual, that will happen from 1231 to 1360. So for now, let's set the first flight mode to hold, and we'll talk about what these are in just a second. And then set the rest up to manual, and then hit save there. And now let's go to the data screen. And when you change that knob, there we go. You'll see the control mode is changing now. So we're going to now go out to the field and test a couple of these control modes. All right, now we are out in the field. It's finally time to start driving the rover. So we got our setup here, got the laptop for a ground control station, got our controller, extra battery. Let's do this. Now, the rover is currently battery powered up. So let's start out learning about the hold mode. Now let's power on the RC controller. Okay, so this knob right here is the one that is currently set up to control the flight modes on the rover. So turned all the way counterclockwise is what we set up to start out in hold mode. So with that in hold mode, and you could also confirm that by looking at your mission planner connected through telemetry. So how do we arm the rover? Well, very simple. You just take the steering stick, this one that goes left and right, and you hold it all the way to the right, and you'll hear a beep. I don't know if you heard that, but that now means the rover is ready to be driven. Now, if you hold it all the way to the left, it'll disarm, okay? So conventionally, the hold mode is really just there so that you can arm in a safe mode, because in hold mode, the rover doesn't respond to any throttle commands or steering commands. It just centers the steering wheels and lets you arm it. Just think of that like, you know, it's you turned on a parked car, right? The motor's running, it's ready to go, but you need to shift modes. Okay, so next up, we're gonna look at the manual flight mode, or rover mode. So that is, we configured the flight mode to be directly next to hold mode. So let's go ahead and arm the rover, going all the way to the right. Mine is already armed, and then shift into manual mode. Now, if you look at the rover, it will actually respond to steering commands. It's going left, it's going right. If I throttle up, it'll go forward. If I throttle back, it'll go backwards. So this command is this drive mode is very simple. So I'm controlling the rover now in manual mode. It's very simple. It just responds to the commands that I am sending through the RC controller. Nothing fancy going on here, but this is the ideal mode just to toy around with the rover in. This is the manual mode. All right, so now we know a little bit about manual mode. Let's talk now about the guided flight mode. This is a very important flight mode. Essentially, it puts the rover into a state where it's just waiting to be commanded to do certain drive commands. So we can set that how we did previously by going to setup and then flight modes. But if we have this ground mission planner set up, we can also change modes a different way. So go to Actions tab and then check out Guided and hit Set Mode. And now you see this change from manual to guided mode. Okay, and now what are we doing here? Well, I said the vehicle is essentially waiting to be commanded to move. And the commands can come from many different sources. One could be simply mission planner. So right now, Wally is in the parking lot. And let's say I want Wally to drive, you know, right here. I would right click on the map and say fly to here. And the altitude doesn't matter because we're not dealing with altitude. So you just hit enter. And there is Wally driving to that waypoint. And now the speed is currently at 1 meter per second. And that is what we set up with WP nav, or the WP speed. All right, now let's try to get Wally to drive back. All you have to do is do the same thing we just did, and the rover should now drive to that waypoint. So this is a very handy method. We can also use the guided flight mode to control the rover with Python scripting, and we will get into that at the end of this video. But yeah, that's essentially the guided flight mode. Okay, next up, let's test out the auto control mode. It's very similar to guided flight mode, but think of guided flight mode as giving you dynamic mission capability that is also autonomous. So the mission doesn't have to be pre-planned. Now, with the auto flight mode, you can still have autonomous driving functionality, but the mission has to be pre-planned. Okay, so maybe, you know, if you wanted to mow your yard with the rover, maybe that could be a pre-planned type of mission, whereas maybe a delivery mission would need to be more dynamic. So let's set up a basic mission for the auto flight mode. It's pretty cool and pretty easy to set up. Just go to Plan in Mission Planner and click on the screen. Oops, I don't want that waypoint. Click on the screen to trigger a waypoint to drive to. And you see that waypoint populates here. And you could just create a little mission. So I'm just going to have it drive to waypoint 1, waypoint 2, drive to waypoint 3, and then go to waypoint 4. So these are simple waypoint commands. You can also tell it to do other things like set a servo at a certain point or control the yaw. But once you have your mission planned out, okay, then you would just hit write, and you're gonna write that autonomous mission from the laptop, your ground control station, to the rover. So now, anytime you trigger the drone or the rover to go into autonomous mode, it's going to run this mission. So now if we hit, again, change the mode in Mission Planner, now let's go over Auto and click on Set Mode. We should see the rover begin its mission. Oops. There we go. So he's going to waypoint 1. And hopefully can make a good turn. There we go. Now heading to waypoint 2. And again, we could speed up this rover speed with those parameters. I believe it's WP speed. This particular rover tops out at about 4 meters per second. It's currently set to 1. But I just like, you know, a little bit smoother of a mission. Now it's heading to waypoint 3, I believe. And this is all, you know, by itself. I'm not controlling it at all. This is just the ArduPilot firmware running our mission. And then you hear a little beep when the mission has completed. It went boo, boo, boop. It was a little beautiful sound right there. So okay, now the last mode we're going to look at is the RTL drive mode. And let's actually set up our RC controller to be able to trigger this mode, because we have a little bit more range on the RC controller than we do with the telemetry modules. And we need the telemetry module connection to set flight modes from Mission Planner. So go into Setup Flight Modes, and Flight Mode 6, let's set to RTL. And then hit Save Modes there. Now, whenever we turn that knob on the RC controller all the way clockwise rotation, we will be in RTL mode. Now, what is RTL mode? It stands for Return to Launch. So, whenever you arm the drone or the rover, it saves the location it's at as the home waypoint. And if you drive around a little bit and then you switch into RTL mode, the rover is automatically going to drive back to the waypoint it was armed from. So let's go ahead and test that out. So right now I'm going to start out in hold mode, and well, we're actually still armed, so let me disarm and then rearm again. You would want to arm, you'll hear it beep. There you go. Now I'm going to switch into manual mode. I'm just going to drive around a little bit. Oops. Just going to drive around a little bit. A little hard to film and drive, but you know, we're doing it. Okay, so now let's say, you know, I don't want to drive back. Wally, come back to me. Come back. All you have to do is switch into RTL mode on your RC controller. So I'm going to do that right now. And here we see, again, I'm not driving it. The rover's going to drive back to the home waypoint all on its own. One thing to note is it will take the quickest path from where it is to the home waypoint, regardless of if there's any obstacles. And that, it can be a problem. So the folks at ArduPilot developed a flight mode called Smart RTL, which essentially means the rover is only going to return to launch based off of safe paths that it knows it's already traveled. All right, so now we have done some really basic control of the rover, but nonetheless, pretty cool to be controlling the rover with different flight control modes. Now we're gonna start getting into a little bit more advanced stuff. So in the past, we have used the Pixhawk for flight control, and we've used the Raspberry Pi as a companion computer. Link them together, and we see we can do pretty interesting stuff with that, like taco delivery, like 4G drone control. You can do a lot of stuff with this combination. In this section of this video, however, we are going to work with the Jetson Nano as our companion computer instead. Now, comparing the Raspberry Pi and the Jetson Nano, they're very similar in a lot of different ways, right? The processor, it has very similar processing speeds, same amount of CPU cores, very similar peripherals. The main differentiator here is, you might notice, there's a huge honkin' heatsink on the Jetson Nano and nothing really here on the Pi, and that is because there's an extremely powerful GPU on the Jetson Nano. It actually has 128 cores on it, so it makes it a really interesting device for onboard artificial intelligence, machine learning, things like that. Now, I mean, there's pros and cons to each one of these boards. The Pis are actually becoming more expensive than the Jetson Nanos, but the Pis have really good community support, whereas the Jetson Nanos, kind of mediocre, right? But they're incredible devices, very powerful, probably more powerful than the Pi. So that is what we're going to be doing in this section. We're going to be linking up these two devices, and I'll show you how to control the Pixhawk from the Jetson Nano. And if you can communicate to the Pixhawk from the Jetson Nano, you can control your vehicle. So it's pretty cool. Once we have that communication bridge, we can do anything, really. We can do simple things like Python-based control of the vehicle, like we've shown you in the past on the Pi with copters. We can do artificial intelligence, OpenCV, so many different things. So let's just get to it. Okay, the first thing we're going to do to set up the Jetson Nano is set up the SD card that'll hold the operating system image. You can find that at the NVIDIA Jetson Nano documentation, which I will link to. You can get away, it says, with a 32 gigabyte SD card, but it recommends you go with 64 gigabyte or higher. So I'm going to be going with 64 gig. Now, here is where you get the operating system image. Now, this is a pretty large file, but I'll link to this URL. So you just click here, and it will begin a very long download. And once it's done, we need a way to flash this operating system image to the SD card. I like to use Etcher. You can use whatever you want. I want to go with Etcher in this video. So I'm going to open up my etching software. Okay, so we're going to flash from a file. And after you extract the Jetson Nano image, the image name is SD-blob. So we're going to select that from the download and then select target. I am going to select the SD card that I have plugged in, select, and then hit flash. So it's about 20 minutes. So kick your legs up, do some scrolling on the phone, and then, in a blink of an eye, 20 minutes will be by, and we'll be ready for the next part of the video.
6.5 hours later.
All right, then once that is done flashing, we have to insert the SD card. Now, it's a little bit hidden on here. You see here underneath this little huge heat sink, you have a slot right there. So with the electrodes pointing up towards the heat sink, you just kind of slide it in there, and you should feel a little click. Now you're good to go. Now this has a giant GPU, so we're not going to be setting this up in headless mode. we're actually going to be hooking it up to a monitor. So first thing we need to do is plug in the HDMI cable. There we go. Then we'll need a mouse to control it. And then the keyboard, we'll need a keyboard, obviously. And unfortunately, on the Jetson Nano, there is not a built-in Wi-Fi wireless interface. So we actually need to plug in the little wireless adapter that comes with the Jetson Nano, so it's not a huge deal. You also have access to the Ethernet port if you'd rather get internet that way. You always need to flip it 3 times before that goes in. And the last thing we need to do is power up the Jetson Nano. The main power is through the USB-C port right here. Again, that's 5 volts and 3 amps. You can also power through the GPIO pins if you wanted to do that, which actually works out on our build. But for now, we're just going to plug in a little USB-C slot and power this thing up. And once you power up, you should see a light right here. Right now I am booting up the Jetson Nano. We'll get to this little splash screen here. It might take a little bit of time to fully get booted up. All right, then once you see the beaver, that means you're at the setup window. So we just have to run a couple of initializing steps. So we're just going to accept the terms and conditions, because who reads those? And select your language. Now we can connect to a wireless network. Mine is Concrete the Lame, so I'm going to connect to that. So anytime the Jetson Nano sees this network, it'll automatically connect. Now here, you'll want to remember what you put in here. So I'm going to say my name is Caleb. Your computer's name, I'm going to name mine Drone Dojo. Then my username, I'm going to say I am Caleb Berg. And then password, you'll need to remember this because at some points it will be nice to SSH into our Jetson Nano remotely, so we don't have to have a visual interface. And you'll do that with your username, the IP address that is assigned to us, and the password you set up for this username. So definitely remember your username and password. Partition size, make sure this is the maximum size, and that will be there by default. Swap file, definitely create the swap file. And then delete unused bootloader partitions, go ahead and do that. And that step will take maybe 2 minutes. After that, just hit continue on the default. And most of your operating system configuration steps should now be complete. So just let this finish out, and then after it's done, you'll want to do a reboot. Now we can log in to the Jetson Nano, and this is Ubuntu. And here we are. This is the background of the Jetson Nano. One more thing I like to do right when I start out is activate my mobile hotspot on the phone and connect the internet to that. So mine is Dojo phone. I'm going to do that. Just set up that connection now. And once that connection is established, the Nano will automatically connect to Dojo phone, my mobile hotspot, anytime it detects it, which is really helpful for when you go out into the field and you don't have, a visual screen. You can just activate your mobile hotspot and the Jetson Nano will automatically connect to that. Okay, so now I am here on the Jetson Nano, pulled up a terminal. You can do that with hitting Control, Alt, and T at the same time. And we just have a couple dependency installations we have to run. So let's just jump into that. So the first thing we want to do is run an update. We'll do sudo apt get update, and this will take a little bit. Just let it do its thing. And then after that's done, we're going to install a bunch of things with apt-get again: Python pip, Python dev, screen, Python for Python LXML, and git. So I might link to that if I'm feeling nice, so you guys don't have to type all this. No promises though. So run that up, or what? Oh, has to be apt, not apt-g. Sudo apt-get install. All right, so we installed a bunch of things with the apt-get package handler. Now we're going to install some things with the pip Python package handler. We're installing Future, PySerial, and then the big ones are DroneKit and MAVProxy. These two programs allow us to communicate with the Pixhawk from the Jetson Nano. So those are the big crucial ones. Okay, then once that is done, we have one more thing to download. Let's first make a directory. We'll call this repos. A little bit of foreshadowing there, a little bit of 3-second foreshadowing. Then we'll cd into repos, and we're going to download a repository from the Drone Dojo GitHub, which is called Python-dronekit. We can do that with git clone, https, and then we're just typing in the URL of the repo you want to download. I know it says Python-dronekit. That's because this repo was initially comprised of scripts for a drone that had a Pi. Raspberry Pi is the companion computer, but it has since grown into a Jetson Nano companion computer with a Rover vehicle type. But a lot of the scripts still work, so don't worry about the weird name. And that will have downloaded now. And if we go into Python-dronekit, we have 4G drone. You can ignore that. Camera, some stuff in there will be useful. DK is short for DroneKit, so we'll go into DroneKit, which is, think of DroneKit as an API into controlling your vehicle, in our case a Rover. So you see there's two different vehicle types here under DroneKit, and under Rover you're going to have a bunch of example scripts. So there's one script on location-based movement, velocity-based movement, and some other fun things. That precision parking Aruco mission that I showed you at the beginning of the videos there. So we're going to run over some of these scripts now. All right, so now it's time to physically connect the Jetson Nano with the Pixhawk. You'll need a cable like this with a DF13 6-pin for the Pixhawk, and these 2.54 millimeter connectors on the other side. I believe you can also connect from micro USB to micro USB here on the Pixhawk, but I have not tested that yet. So very simple on the Pixhawk end. Plug in the connector, and this should already be plugged in on your build, but you'll plug in. It's hard to do with one hand. Voila! Okay. The red is going to be toward the left of the Pixhawk. Ground is right on the Pixhawk. You can plug into either TLEM 2 or TLEM 1, doesn't matter. And we are establishing a UART connection with the Jetson Nano. So let's find VCC, the red, and the pinout is actually kind of labeled here on the side, which is pretty handy. We're going to plug VCC red into the 5-volt line, and then after that is ground. So grab the black wire and plug that in. There we go. Next up, we are going to plug the blue wire in directly above ground. And then last but not least, grab the white wire and plug that directly above the blue wire. And now we should be able to communicate across this UART bridge to the Pixhawk from the Jetson Nano. One more thing that I do like to do is sort of make each one of these individual 2.54 millimeter plugs into one by just tacking a little bit of hot glue across all four, so it becomes one unit. It's harder to rip out. Not required, but it might keep this plugged in a little bit better. Okay, I'm back into the Jetson Nano. Let's go ahead and test that connection that we just established. So I'll open up a terminal. Now the first method, as I said previously, is going to be MAVProxy. Now MAVProxy is a command line based ground control station. So how do we access that? Well, on the Jetson, let's start out saying sudo MAVProxy, and we should be able to just hit tab after typing some of that, and it'll auto-complete. Then -- master. Here, we're trying to feed into MAVProxy the device or IP address we should be using to communicate with the Pixhawk. Now, the UART device on the Jetson Nano is called /dev/ttyths1. Okay, so that is the UART device that we just wired up. So if we hit enter here and enter in our password, this should establish the connection with the Pixhawk. As you can see, we're in. So we're using, on this particular Pixhawk, ArduRover 3.5. We could do things like change the mode manual. See, now I'm in manual mode. And one note about what we just did is we had to use sudo to initiate this command because only sudo users can use that UART device. So that's the MAVProxy connection. Now let's try to connect with DroneKit. And DroneKit is cool because that's Python scripting controlling the vehicle. So let's go into repos that we downloaded, go into PyDrone scripts, go to DK, and then go to Rover. And here we have a couple of Py scripts, DroneKit Python scripts. Let's start by typing sudo python connection test, and so that's going to launch that script. And this script also needs to know which device it should use to communicate with the Pixhawk. So how do we do that? We do --connect and then enter in the device. So it is /dev/ttyths1 and hit enter on that. And here we go. The script output that the AutoPilot version is APM-Rover 3.5. And then some of the code was trying to arm the vehicle, which nothing's attached to the Pixhawk, so it couldn't arm. Let's go ahead and look inside of the connection test. And it looks like a Python file, right? We have our dependencies we import at the top. We have the function for connecting to the copter. And after we establish that connection, we get a vehicle object. And this vehicle object, we can get information from it. So what state is the vehicle in? What are some of the parameters? And we can also write commands to it. So we could command this vehicle, hey, move forward at 1 meter per second, or go to this waypoint. So once you're successful testing this connection template, or this connection test.py file, we're ready to jump on into some more advanced DroneKit Python stuff, and that is actually commanding the vehicle. Now we're going to explore some of the DroneKit capabilities. Some of you might already be familiar with DroneKit controlling a drone, if you're familiar with the channel, but now we're going to dabble a little bit with controlling a rover from Python-dronekit. Now there are 3 main ways to control the drone. First way, let's think of this as location-based movement. So we have a waypoint we want the rover to drive to. We program that with code, and the rover drives to that waypoint. The second way we have to control the rover is through velocity commands. Now think of this as, there's no intended destination. We're just saying, hey rover, Wally, drive 1 meter per second, and then turn left at 2 meters per second. So you have velocity-based commands that we're also going to go over. And we also have a third way, not really recommended because it can be a little dangerous, but it's RC overrides. So, when you're driving manually with your RC controller, this is me pantomiming RC control, you're sending RC PWM waves to the receiver that tells the drone or the rover how fast it should be driving. You can simulate that from a DroneKit Python script. I wouldn't do that though. I would stick mainly with the first 2 methods. So that's what we're going to go over now. One cool thing, again, people that are familiar with the Drone Dojo probably already know this, but you can actually simulate DroneKit missions on a simulated computer version of the rover before actually taking that rover out to the field. So this is really good debugging exercise to just make sure everything works perfectly on the simulated rover, and then if it does, then you can port over that code to the real rover. So we're going to do that now. We're going to start out with location-based movement. All right, so I am going to launch my environment for testing my DroneKit rover scripts. I'm doing that with a virtual machine. It's a little bit of a process to set up, but once you have it set up, you don't really have to change a lot. Now, I actually do have a course that teaches on a sort of programming simulated vehicles, how to control with DroneKit, any vehicle type from DroneKit. And that course offers this pre-configured virtual machine that has all the dependencies ready to go, everything you need, so all you have to worry about is the programming. So I'm going to open up a terminal here, and it's good to test the code on the same simulated ArduRover version that you're running on the real version. So on my real rover, I'm running with ArduRover 4.1.0. So I would download that version onto my virtual machine with GitHub. So you could do that with git clone -b to specify the branch, and then type rover 4.1.0, and then the URL of the ArduPilot repository. After that would finish downloading, you would go into it. It should be ArduPilot. I already renamed mine to ArduRover 4.1. And you would type git submodule update --init --recursive. So then you are ready to launch a simulated vehicle. Now so we're matching the version type on our simulated vehicle and the real vehicle. I also like to match the same geographical points that I'm going to be testing on. So I know where I'm going to be testing on in the real world. So I want to make that a place I can test on the simulated world. Listening to some K-Dot. Has some K-Dot. So I am going to be testing out in this field. And let's make this right here my home waypoint. So you can just pull up Google Maps, find your latitude and longitude coordinates. But here is a little bench that I get to sit on. So this is going to be my home waypoint. So how do I use that as a launch point in the simulated world? Well, very simple. Just go to gedit, tools, autotest, locations.txt, and you'll go to the very bottom. You'll enter in a name, so you need to name the location. I've actually already input this for me. Name of the location, OK Rover, and then equal sign, then your latitude coordinates, comma, your longitude coordinates, the altitude, so 0 for me, and then the position of the vehicle. So north is 0 degrees, east is 90. I want my rover to face west, so I put 270, and then you would hit save there. So remember, OK Rover is that location. So now I want to launch the simulated vehicle. How do I do that? And again, this is just a crash course on this subject. If you want a more in-depth knowledge of what I'm teaching here, I definitely recommend you check out the Drone Programming Primer, which also covers rovers. So it's just enlightening about the software stack in general for ArduPilot vehicles. But how do you launch simulated vehicle? Well, you could go to, you want to change directories into the vehicle type that you want. So I'm going to cd into rover. Now you type -- tools autotest sim vehicle. Okay, so now we feed in some options. So -L is for location. And what location? Well, I want the rover to launch at the GPS coordinates of that waypoint we just entered. So OK Rover. So this is the test area. And then -- map will load up a map of the simulated vehicle, and then -- console. Okay, so this is booting up the simulated vehicle. Now, if it's your first time booting up the vehicle, it will take some time. It has to compile all the code and all that fun stuff. But here we go. You see the rover has launched at my home waypoint that I'm going to be testing at in Oklahoma. Normally it launches at an Australian little airfield. So here we are. Now, the vehicle's up and running. So think of this as like, this is the Pixhawk or the flight controller up and running. So let's pull up another terminal, and now let's connect a DroneKit script to this simulated flight controller. So in this pre-configured virtual machine image, all these scripts are already ready to go. So I'm going to gedit into rover location based movement. Okay. Now, this script is already on the rover because you downloaded my repository with Python scripts. So I'm not going to go over all these little commands. I mean, very quickly. Connect my copter connects the script to the drone or the rover. Arm just arms the vehicle. And then go to drives the rover to a waypoint. And then waypoint, here we can create different waypoint objects we want the rover to drive to. So I'm starting out here. Let's say we want the rover first to drive to this waypoint right here. So we can actually click on the map, and it saved our click here. So these are our lat and long coordinates that we'll enter into waypoint 1. Okay, so waypoint 1, 36.005765. Waypoint 2 is negative 95.86.0332. And then let's say we're up here a little bit. Let's like make a little triangle. Let's drive here. There's my second click, so we'll put that into waypoint 2. And now let's maybe drive down here. It's gonna be a little triangle we're drawing. There's my third click. So these are our 3 waypoints we want the rover to drive to. Then we connect the vehicle to the script, our Python script, which will be on the Jetson Nano. And here you can actually set parameters from DroneKit scripts. So remember, we were setting a bunch of parameters with Mission Planner. You can also do that from a DroneKit script. So I'm setting the speed of the vehicle to be 2 for 2 meters per second. Now I'm arming the vehicle, and now I'm calling the goTo function, which allows you to feed in a waypoint that the rover will drive to. So it's going to drive to waypoint 1, waypoint 2, and then waypoint 3. After it gets to waypoint 3, I put the drone or the rover into RTL mode. So the rover will automatically drive back to the home waypoint. Yeah, that is the gist of that script. Very basic script, but it shows you, the building blocks of more advanced scripts. So we have the ability now to drive to waypoints. Let's go ahead and run this script. I'm going to X out of that. And let's launch that. So Python Rover, Red Rover, and -- connect. On the simulated vehicle, you're going to be connecting to a IP address and not a device. So it's 127.0.0.1, and then the port is 14551. Hit enter there. And here we go. The DroneKit script now has the reins of the rover. And the rover's in guided mode. Remember, I told you that guided mode means the rover or the vehicle is waiting to be commanded. Well, the vehicle's in guided mode and it's being commanded now by the script, the DroneKit script. So it reached waypoint 1. Now it's going to drive to waypoint 2. And you really can't imagine how helpful it is to be able to stage your missions that you wrote for your vehicle, your rover, on the simulated world before you do it in the real world, because God knows how many problems or bugs you're going to have to debug out in the field that you could have just found on your simulated rover. So it saves a lot of time, saves a lot of headaches, and actually it's a lot more safer. I mean, rovers aren't very dangerous, but if you're doing something with a copter, it's just definitely recommended to stage your scripts on the simulated vehicle before taking them out to the field. So there we go. The drone went to waypoint 1, 2, 3. Now it's in RTL mode, so it's automatically driving to the waypoint that it was initially armed from. So now that we have confirmed that this script works, we are safe to go out into the field and test this on the real rover. Now again, this script rover location-based movement will already be on your rover, or on your Jetson Nano. So all you have to do is enter in the waypoints that you want the rover to drive to. So let's go out into the field and do that now. All right, so now we are out in the field with Wally the rover, and we're gonna run that same script we did on the simulated vehicle in the simulated world. In the real world, there's that bench I was telling you about when we were in the simulated world. So yeah, we're going to run that location-based movement drone kit script on Wally. I have activated mobile networks, or the mobile hotspot that is connecting the Jetson Nano with the laptop, so I can communicate with the two. If you need help with that, check in the top right of the screen. I have a quick video on how you can do that. Okay, so we're gonna go to repos, Python scripts, DK, Rover, and we'll show you the scripts here. So I've put in those triangle waypoints into rover location-based movement, so I'm going to trigger that script. So I'll type sudo python, and then the name of the script we want to run, rover, and then we'll connect with that UART device, which is /dev/ttyths1, and we'll hit enter there, enter in our password. It might take, a solid 10 seconds for the drone kit script to connect to the Pixhawk, but once it connects, it should throw the rover into guided mode. And there we go. Rover is now armed, and it should be driving at, I think it's 2 meters per second is what we set the parameter to, WP speed, in the drone kit file. So it's going to waypoint 1, pretty far out there. Come back, Wally! Wally! All right, Wally's realizing the mistake he's done, the good life he has. He's turning around in life, trying to come back to me. Going to waypoint 2. And remember, once it gets to waypoint 3, we actually change into RTL mode. And RTL mode operates with a different speed. It doesn't use WP speed, it uses RTL speed, I believe, which is set to 1 meter per second. So once it gets to waypoint 3, which it should any second now, it'll trigger RTL mode. And you should see it slow down a little bit, drive a little bit slower. So he's worn out from his long mission. He's coming home. Come back to the good life he has with me. And once we get to the home waypoint, it'll automatically disarm, and that is a successful mission. All right, now we know about location-based control. Now let's check out velocity-based control. So here is another script for drone kit, and this is for controlling with velocity. This should also be already on your Jetson Nano if you installed that repo. So here we have two methods of sending velocity commands. One is a local velocity command, and the other is global. Now, what is the global velocity command? Well, we have 3 axes, right? X, Y, and Z. With the rover, we don't have to worry about Z, right? Because we're just dealing with 2 dimensions. So we have the X axis and the Y axis. Actually, on our rover, the X axis is north and south for global NED velocity commands. And what is NED? think north, east, down is the sign convention. So north is positive, south is negative. So east is positive, west is negative. So north and south is for Vx, east and west is for Vy. So if we wanted to move the rover true north, we would send a positive number to that first variable Vx, and it would move true north. And then true west would be sending a negative number to the Vy variable. True south, you get the idea, right? One thing about these velocity commands is if you want the drone or the rover to keep progressing at this speed, you need to send this command. I think it's every second or every 2 seconds or something like that. So if you send the command once and don't send any more velocity commands, the vehicle will stop. So you need to be looping the velocity commands and sending them over and over again. So that is the global velocity command. Next we have the local velocity command. Now local means it's local, it's relative to the heading of the rover. The heading meaning which way is it facing. So now if I send in a 1 for the local velocity command, the rover isn't going to move true north, it's going to move forward relative to where it's currently pointing. So here, the way our rover is currently, it would drive to the east, true east. You actually can't send in a negative number for the local net velocity to the Vx. You would think it would just reverse, but it doesn't do that. It spins in circles. Now, how do you turn? Well, that's where you feed into Vy. So sending in a negative number to Vy turns the rover counterclockwise, and sending a positive number turns it clockwise. Let me fix that. Okay. And then last thing I'm going to go over here is the backup. So we actually don't have an easy way to just reverse the rover, to drive in reverse. Because you'll notice when we do these commands, it's always driving forward. So I wrote a little script that actually does something bad, something naughty. It's using RC overrides to manually reverse the rover. This is the only time I would really recommend using RC overrides. And you'll see how this works. But essentially, you know, we're putting the rover into manual mode, which responds to RC input, and then finding the throttle channel, writing 1400 to it, so it'll go in reverse for 1 second, might even make that 2 seconds, and then bringing it back to 1500, and then putting the drone back into guided mode. So this function is also already on your Jetson Nano. So let's go ahead and test this script out before we head out to the field to do it. So we'll just do the same thing. Now you'll see the rover's moving true north. Now it's moving true west, true south, and true east. Okay. Now we're moving north relative to the vehicle. Now we're moving counterclockwise. Now we're turning clockwise. Okay. Now we're moving in reverse with that command that I showed you with the RC overrides. And you'll notice the rover's actually reversing. It's not trying to point the front of the vehicle to where it's heading. It actually lets you drive in reverse. So yeah, let's go ahead and run this out in the field now. Okay, so now we're going to run the velocity mission that we tested and staged on the simulated rover. So let's go ahead and hit enter and check that out. All right, it's going north, going west, going south, and heading right at me. And now it should be doing its local velocity commands. Now it's turning different directions. Now it's reversing. And there we go. two little reverses. And if you want it to reverse more, you could always increase the time that it reverses with that manual RC override, or set the RC override to a more aggressive value. I'm only going down by 100 pulse width modulation values. But yeah, that is the velocity-based drone kit control. One more thing to note about the local velocity command and the VY axis, or the VY variable. The turn rate gets more aggressive, or the turn angle gets more aggressive the higher value you enter in. So if you put in like 0.1 for the turn rate, it would barely turn, and if you put in like 3, it would turn super aggressively. Okay, so now we know a bunch of different ways to control the Rover. You got the RC controller, you got the auto mode, Python-dronekit scripting. Now we're gonna do a little bit more of an advanced Python-dronekit script, and we're gonna do a little Rover delivery mission, which is turning out to be like the hello world of drone dojo robotics. Cut to Buster making his taco delivery. Oh, but instead of delivering a taco this time, we're gonna deliver a 5-hour energy. Got a little clip on there, and how are we gonna do that? Well, one of these cheap little servos gives us the ability to hold on to an object and let go of an object. And actually, it plugs in pretty simply to the Pixhawk. So this light orange or yellow color is signal, the brown is ground, and signal goes down on the Pixhawk. So we're just gonna plug this into aux out 1, which is actually servo 9 in the code. So it just goes like that. Then we'll mount this at the front of the Rover, and then I'll show you how you can control it. Okay, now on my Rover, I installed the servo up at the very front of the vehicle and wired that back to the Pixhawk. A bunch of wires going on, that's why I showed you how to connect it before I installed it, but it is installed right to that aux 1 port. And you will have to put the horn on, and after you do that, you should pull up Mission Planner, and you can actually control the servo through Mission Planner. So all you do is go to servo, and then the servo we plugged in was aux 1, which is the same as servo 9. So if we can actually toggle the position of the servo with these buttons, low, mid, and high. So if I go low, the servo is now low, and then I'm gonna go click high. Now the servo is high. Now you can test out what is high and low on your horn, and then rearrange it so that the up position is at about a 45-degree angle, and the down position is at about 45-degree angle. And then you can simply put a clip on there or some other way of attaching to a deliverable object, and we can test this out. So we're high now, and then we hit low, and now we dropped off the object. And then there's the midpoint. So we can control the servo manually through Mission Planner, but we can also control the servo through DroneKit scripting. So we're gonna go check that out right now. Okay, now I am on the Jetson Nano. Let's go to repos, pydrone scripts, DK, and then go into drone. Now there is a script in here called controlservo.py. Let's go in there. Now this is the DroneKit way to control a servo. So high, you know, the pulse width modulation can be from 1000 to 2000. So high, let's just put it at 1900. Low is going to be 1100, just so it doesn't go beyond the limits of the servo. And remember, our servo is 9. And then the connect, if you want to enter it in manually, is /dev/ttyths1. Don't really have to worry about that. This is just for me to show you what's going on. So then, control servo. This is the function we're going to use in our delivery mission. And very simply, you just enter in the servo you want to use, and then the value, so high or low. And then this is a mavlink message that gets sent to ArduPilot called mav command do set servo, and it inputs those two values, sends it off to the vehicle. So that's our function. Then we'll use it here below by first setting the servo high, and then setting the servo low. All right, so now we have all of the core ingredients available to us to do our rover delivery mission. Let's go ahead and write that up. So let's go into Rover, and we're going to use the rover location-based movement script as a template. So just copy that, and then I'm going to create a script called 5hour deliver 5hour.py. I've already created that, so I'm just go into that. And the control servo, let's go ahead and set up some servo variables here at the top. Servo number, mine is 9. Servo high is 1900. Servo low is 1100. So when we drop the servo low, it'll drop the object. When it raises it high, it'll hold on to the object. So we know how to control the servo from Python-dronekit. We know how to drive to various waypoints autonomously. Now let's just grab our waypoints. So let's plan out this mission. So back out in the field, I like to keep this as my starting point. There's a nice bench here, you know, not that far from the parking lot. So we're going to start here, and then this will be our first waypoint. I'll click there. So here is our coordinates. I'm going to go ahead and enter those in to waypoint 1. We'll make that waypoint 1. And then waypoint 2, there's actually a nice little bench over here that I'm going to be waiting at to get my 5-hour energy. So this will be waypoint 2. Let me click here again. So let me input waypoint 2 into our script. And then we don't actually need a waypoint 3. So this is our home waypoint. This is waypoint 1. Here's waypoint 2. We're going to launch from here. The rover is going to then drive to waypoint 1. Then I'm going to drive to waypoint 2. And then it's going to loop back, drive back to waypoint 1, drive back to waypoint 2. Then when it gets to waypoint 2, it's going to drop off that 5-hour energy with the servo. So let's go ahead and write that mission into code form. We have our waypoints. We know how to control the servo. So what do? So we're going to establish a connection between the Python-dronekit script and the rover. So that's that. We're going to set the speed. And initially, we're going to make sure the servo's high. So we're going to raise the servo high, control servo, and then we'll wait a little bit. And right here is when we will attach our object to the servo. Okay, and now let's arm the rover. We're going to go to waypoint 1, go to waypoint 2. We don't need a waypoint 3. Remember, at waypoint 2, we're going to drop the object. So all we do is write. Okay, so then we will just go back to waypoint 1. Remember, waypoint 1 is right here. So we'll just go to waypoint 1 again. And then from there, we have a straight shot at our launch location. I'm just going to write a return to launch, which will just drive the rover from here to here, the point at which we armed from. So I'm just going to put the vehicle into RTL mode, and that will be the end of the script. This is our very simple drone delivery script, or rover delivery script. Okay, so we are out in the field now, ready to do that rover delivery mission. We got Wally out there, ready to go. Got the laptop here, and we're all connected Jetson Nano to laptop with the mobile hotspot configured. Of course, we got the 5-hour energy ready to be delivered. Got a better clip there that'll hold on to the servo. And now we just have to run that script. So we're going to start out running deliver 5hour.py. And once that script connects, just a reminder, that servo is going to go into the up position. So currently the script is not connected yet. And then once it shifts up, we have about 10 seconds to place the 5-hour energy on the servo. Come on, wake up, Wally. Wake up. Oh, the servo went high. Oh shoot, oh shoot. Okay, here we go. Oh my God. And there we go. We got Wally driving to the first waypoint. And this is pretty rough terrain. Not really mowed too much over here in this field. But you know, that's what crawlers are good for. They're good for all sorts of different terrain. Hard to keep up with you, Wally. Still holding on to that 5 hour. You know, Wally's he's a good kid. I was hard on him earlier. He tried to run away from me, but you know, he's still young, he's still learning. Now he's being helpful delivering stuff, so you got to give kids time to develop. So once he makes it to waypoint 1, he'll slow down for a second, and then he'll start heading on to waypoint 2. Got a little bit to go here. Still doing pretty good holding on to that 5 hour. And it dropped the 5 hour. And it's gonna head back to that waypoint now. I'm actually gonna pick this up because that's a long walk back.
One eternity later.
Should almost be back to waypoint 2, at which point we'll trigger into return to launch mode. And there we go, we're on our way home. Back to the laptop. And there we go, mission success. You know, so by now, you and Wally, you've been through a lot together, you know? Some could say you were friends.
So me and you are pretty much friends by now, right?
We learned about ArduRover Basics, truck drove by, ArduRover Basics, how to build your own rover, manual control of the rover, autonomous control of the rover, simulated mission planning on our computer, autonomous rover delivery, bunch of stuff. So, like I said earlier, with this rover here, we are really only scratching the surface. I mean, we have a GPU with 180 or 128 cores on it, so there's a ton more you can do with this, but it's a good foundation. So now that we have this foundation, the next video is going to be a crash course on OpenCV influence control of the rover, and that will be using this camera here we have installed on the front. So that video I teased about precision parking, well, I'm going to show you how to do that and a ton more. So after that, we'll be getting into AI-based control, voice commands, obstacle avoidance, a ton of stuff, really just like how you guys want to direct this. And like I said earlier, all of the future projects we're going to be doing are going to be conducted on this Drone Dojo Rover kit. And we do have this available for you to purchase. It comes with everything you need, including the Pixhawk, the Jetson Nano, the crawler frame chassis, the ESC, the servo, just all the hardware you need. But it's also more than that because one, your Pixhawk is going to come pre-flashed with firmware that works and parameters that work, tuning that works. The Jetson Nano is going to come pre-flashed with the operating system, all the dependencies you need, and all of the Python example drone or rover control scripts already on the Jetson Nano. I mean, you just won't find help like that anywhere else or any other thing you purchase. These steps are normally pretty Larry David right there. Pretty time consuming. We're doing this so you can focus on your drone project and not have to focus on all of the other setup crap. You can find out more information about these rover kits in a link somewhere. If you're on this video, you can find it. Okay, the sun's getting kind of bright. Can't see where.
I can't see where.
Can't see where. If you're curious to learn more about the ArduPilot software stack and how to simulate missions right on your computer like we did in this video, I definitely recommend checking out our drone programming primer. It teaches from the perspective of drones, but really all of the core components are the same regardless of the vehicle type you're using. This is how I was able to port over my drone knowledge over to the Rover and start playing around with that so quickly. We also have a dedicated section just for rovers in that course. And it also has, and this is a very important part, a pre-made, pre-configured virtual machine environment that also has all of the dependencies pre-downloaded, all of the example scripts already there ready for you to run. So it's very, very helpful platform for you to test out your missions before going out to the field. So with all that, me and Wally better be getting out of here before Buster the Drone starts to get a little jealous about me and Wally's time together. So I'll see you in the video shortly.